So the whole intent on solutions is what can we do within them. In Gen Chem, you're primarily looking at solutions in water. Okay, so that determines a new phase for you. What's that phase? We have aqueous, which we can specify with an AQ after whatever species we're looking at. If my pen works, there we go. Which theoretically you guys all know already, right? That was a resounding yes, so we'll assume that's true. So when an ionic substance dissolves, it dissociates into the individual ions. So what ends up happening is water comes along, or your solvent comes along, and starts ripping the individual ions away from each other. Okay? And it solvates them. So we have this solution. This process is called our dissociation, and if I set this up right, we even have a nice little video that she attempted to put in. So let's see if it actually works. Oh, come on, do it. Shows up nice and cleanly on the screen there. So we just added salt to water. Stir it. I know, it's exciting. And then if we zoom in on what's actually happening in that process, each of the water molecules comes up to that solid and wraps around individual ions. So when it goes through and does that, what do you notice is happening? Whoops, let's not pause it there. See if I can get one with an ion. What happened? A bunch of what are carrying what? A bunch of water molecules are surrounding an ion. Okay? And technically an anion, right? Yeah. Some of you laughed. It's good enough. Okay? If we take a look at that closer, let's be a little bit more specific with it. It's not just a bunch of waters coordinating around that anion. It's the positive side of the water that's coordinating. When we look at the structure of water, we have the oxygen bound out to our hydrogens. And due to a difference in electronegativity in the bonds between the oxygen and the hydrogen, our oxygen ends up carrying a negative charge, or a partial negative charge, and our hydrogen ends up carrying a partial positive. We show that with those nice little delta symbols. So when we look at water interact with our salt, the water orients itself so that the positively charged hydrogens hook up with the negatively charged anion. When that then interacts, it can then pull that away from the rest of the ionic structure. And we end up getting these individually solvated ions. Let's see if it continued to play. No, it didn't. What happens if we looked at a positive charge? I'll just draw it. There's our positively charged ion. How would it get solvated? We would look at our individual oxygen molecules now coordinating to it. We'd have to be careful when we show our hydrogens to make sure that the hydrogens are not aimed towards the positive charge. Why? They're positive charges. So positive like charges repel each other. So when we draw on our water molecules or the rest of our hydrogens, we would show them aimed away from the positive charge. Does it have to be perfectly away from it? No, not necessarily. But in general, we try and align it as best as possible so we're just seeing that oxygen interact. Okay? So we're getting that nice kind of strong interaction that's now allowing that ion to be solvated. Every time we dissolve a salt, this ends up being what happens. Okay? You're going to complain, aren't you? So, when we take a solution, we're looking at a homogeneous mixture of two or more substances, and typically they're pure substances. That solution is made up of primarily two parts. What do we call those two parts? What's that? We've got a solvent and a solute. So your solvent is the one that's present in the greatest amount. Okay. Typically it's a liquid, but it could also be a gas. It doesn't really matter. Okay. Our primary goal is focusing at liquids. Why do we not look at gas solutions? So we could say that almost all of our reactions involve water, and since our gas solutions don't deal with water, that's why we don't look at our gas solutions. Okay, but there's another reason. Trap a gas for me right now. Grab it. Okay. It's not particularly easy to trap and hold a gas, which makes it very difficult for us to run experiments with. Can we do it? Yes, but within an undergraduate lab, it's not the easiest thing to work with. So most typically, our solvent ends up being a liquid, and even more commonly, it ends up being water, because water is extremely abundant and ridiculously cheap. Any other substance that is now mixed in with this is known as your solute. Okay? So those are your two primary components within a solution. We can now subcategorize and look at our solutes and decide what's going on with those. Okay? The most common thing that's referenced is something known as electrolytes. Okay? Electrolytes are merely ions solvated in water. That's their only process. Okay, why might we call them electrolytes? Because they conduct electricity, so that if we then put in some electrodes and powered a battery through it, we could end up getting light. So we've got electricity and light, electrolytes. There they are. So when we take our salts and dissolve them in water, we can end up forming these electrolytes. But what if we take something and try and dissolve it in water, and it doesn't allow the electric current or a light to come on? Well, we refer to these as non-electrolytes. So there are species that we could add to water that don't turn into ions. They still dissolve, but they don't give us this ionic formation. And it's that ionic formation that gets us the electric current passing through it. Okay. Whoops. I'm going to dump back there real quickly. So let's take a look at some examples. An electrolyte. What's a classic electrolyte?
Potassium.
Sodium chloride.
Not to rip on your potassium. Potassium was a good choice too if we went at potassium ions. So sodium chloride. You take a solid white powder of sodium chloride, you add it to water, it's now an electrolyte. We get the ions. How about a non-electrolyte?
C6H12O6.
Way to drop out a formula, C6H6O6, also known as sugar.
Sugar H12. Oh, yeah.
No. Why might we look at this example?
Because it's not an ionic substance, so it wouldn't associate it to water.
What does salt look like? Way to just jump the answer. Yeah, salt looks like sugar. We can take a white crystalline solid and we can add it to water. In both cases, what happens when we add it to water? It dissolves. Do we get electrolytes out of both solutions? No. Okay? So it's not just do we have a solution. That's not the be-all, end-all. There's other things that contribute to why sugar dissolves in water. But that process does not involve the formation of ions. How do we get ions? We need to be adding in a salt. And when we use the term salt, we're not saying just sodium chloride. We're saying any compound with an ionic bond, a metal and a nonmetal. Strong electrolytes completely dissociate. So as soon as they hit into water, they completely separate into their counter ions. Okay? We can see this because when we put a battery, 2 wires and a battery hooked up to a light, we'll see that light shine nice and brightly as if it was a solid wire running all the way through. How could we represent that within an equation? Sodium chloride solid. When we add it to water, what happens? The sodium and the chloride separate. Is that it? What's that? Okay, we do need the AQ. Why are we adding the AQ? We're saying those ions are dissolved in water. It's not just sodium by itself or chloride by itself. Okay? It's dissolved in water. The AQ now necessarily implies that water was also involved in this. Is there anything else we could add to this equation? Or rather, should add?
I believe chlorine is a diatomic. Is that correct?
Okay, interesting idea. Chlorine is a diatomic molecule. So anytime we look at the element chlorine, we need to make sure that we're putting it in its elemental phase. So we could go through and write the 2 next to it. Don't write the 2. Why do we not write the 2?
It's not a gas. It's not by itself.
It's not chlorine gas. Remember, the ionic compounds split into the ions. This is not chlorine. This is not sodium. What are they?
Increased solutions of it?
They are chlorine ions and sodium ions. Okay? As a chlorine ion, it is not its elemental state, which means it is not diatomic. How can we add that information into this so that we know that we're talking about the ions and not sodium, the element, and chlorine, the element? We can associate the charges with them. Sodium carries a positive charge, your chloride carries a negative charge. How can we make sure that when we look at this equation that we're not just putting those two things next to each other, that they are actually independent species? Nice and simple, plus in between. How did we know the sodium carried a +1 charge and the chloride carried a -1 charge? All sorts of fun answers on that one. Unfortunately, this is my first time dealing with 151 here, so I don't know what you've been asked to memorize yet. And 130, so we could look at electronegativities. The other thing that you also have to be aware of is that there are certain elements, and those certain elements carry very particular charges. You're required to know those charges at some point during 151. I kind of thought that already happened, but I don't know.
Yeah, it did.
Yeah, you already did. Okay, so you memorize them. What charge is the sodium? +1, because it's in that group 1 column. Okay. So we could look at their charges and have those memorized, and that's where we can then put these values in. What if you haven't memorized the charges? It's an exam. You can't Google it. Nice try. You could move to the even harder aspect and look at their electron configurations. Have you done electron configurations yet in 151? No, not yet. If you took 130, you might remember electron configurations. You could start to predict their charges from the electron configurations. That is a hell of a lot harder than just memorizing. Okay? So memorize those charges if you haven't already. A weak electrolyte only dissociates partially when dissolved in water. This one gets a little bit trickier. Okay? And it's not easy to go through and draw out an example. Okay? But let's take a look at it anyway. Let's take HF. Let's ignore the phase on the starting material for the moment. What happens when we add HF to water? I appreciate your participation, but I think I'm going to have to silence you for a little bit. See if we can get somebody else involved. So we could go through and write out the equation. That's nice and helpful. But when we go through and look at this, looking at that equation, can you tell that it's a weak electrolyte? Why not?
Looks the same as the other one.
It looks exactly the same as the other one. Right? That makes this a little bit more difficult. Okay? So how can we tell the difference between a strong electrolyte and a weak electrolyte? Periodic table. H is still in that first column. F is still in that seventh column. We need a little more than that. How do you know it's a different type of compound?
Because hydrogen and fluorine are both nonmetals, and chlorine is a nonmetal, but sodium was a metal.
So you could try and classify your compounds according to their naming equivalents. When we look at HF, what type of a compound do we have? Covalent compounds, or a molecular compound. When we looked at sodium chloride, we had an ionic compound. That's a big tip-off that can help us go through and potentially solve these. Right? How could we add information into our reaction so that we know it doesn't completely ionize? This is a tricky concept. In fact, we spend an entire semester talking about this. That's your next one. What does this arrow mean? We go from the reactants to products. What if I want to say it doesn't go all the way to the products? I can now use two arrows. One arrow going to the right towards our products. You'll notice what's special about that arrow going towards our products. It's very small. The one on the bottom going towards our reactants. Very, very big, saying that our reaction favors the reactant. So we could add information into this. Okay? What do we expect you to do? We expect you to memorize. Lucky you. Okay? So how can we come up with ways to figure out what our strong electrolytes versus our weak electrolytes are? Okay? Well, there's some classic examples of strong electrolytes. Your strong acids. There's your first hint. It says strong in the name of it. It matches. So we've got a whole bunch of strong acids listed out here. All of those are strong electrolytes. We also have strong bases. Strong bases are also strong electrolytes. But when you look at those two sets, we should run into some interesting quandaries. Yes, I just said quandaries. I thought it was funny. When we looked at HF, what did we say? Strong or weak electrolyte?
Weak.
Said it was weak. When we look at HCl, what is HCl? Strong. Remember back, someone suggested that HF was weak because it was a covalent compound. HCl? Also a covalent compound. So our method of trying to come up with some pattern didn't quite work for us. So what we need to know is what's going on with our strong acids. Those strong acids, by definition, dissociate into their ions, and that becomes problematic because those are not ionic compounds. Those are covalent compounds. How do you know what your strong acids are? It's a simple, yeah, go for it. Who said it? They're on that list.
Memorize.
You memorize your strong acids. Right, if you've got the strong acids memorized, you now know. Is HF a strong acid?
No.
No. What does that mean? It doesn't dissociate completely. Our other strong electrolytes, strong bases. We got a bunch of lists of possible strong bases. How do we know it's a strong base? It's on the list. What if you don't have the list? You memorized it. Right? So you are responsible for remembering those. And actually, let's take a step back from that for a moment. Our first example of a strong electrolyte was what? Is sodium chloride on the strong acid list? Is it on the strong base list? Why is it a strong electrolyte? Why does it completely dissociate? Ionic. Interesting idea. Silver chloride. What's special about silver chloride? Is it an ionic compound? Metal, non-metal, ionic compound. Sodium chloride was what? Strong or weak? Sodium chloride, or that other one? Silver chloride? It's weak. How do we know that difference? We went through and started to classify ionic compounds being strong electrolytes, and we said covalent compounds were non-electrolytes, and that didn't work when we looked at our acids and bases. What happens now? That nice little rule where we had ionic compounds always being strong electrolytes is now also an invalid rule. Okay? It's going to come down to solubility rules. Soluble ionic salts are strong electrolytes. How do you know if it's a soluble salt?
Look at the solubility.
You look at the solubility rules. This is a fun next little question. Is this all of the solubility rules? No, not even close. Okay. We've got tons of solubility rules. Which ones are probably the most important? The ones on this list. Okay. Those are going to be important to be aware of and being able to use. Okay, so let's take a look at being able to use these. Let's go right back to our sodium chloride and our silver chloride example. Why is sodium chloride soluble? You got to be able to use the rules. What rule? We follow through our little tables, the soluble ionic compounds in that first section. Take a look at our chloride. Compounds with chloride are soluble. That's what this rule means. Soluble ionic compounds, anything with chloride is soluble, which would say sodium chloride is soluble. Of course, with every rule, what do we have? Exceptions, and what's the very next column? There's our exceptions. So chloride, when it's with anything, is soluble, except when that anything is silver, mercury, or lead. So what does that mean for sodium chloride? It's soluble, which makes it a strong electrolyte. What happens with our silver chloride? It doesn't dissociate into the ions. We're now either in that weak or non-electrolyte system, depending on how you want to classify that. Okay? Yeah?
Is that the specific ionic charges for those elements?
Yes.
That some of those elements might be variable charged? Is there other charges or lines?
Quick scan through. All of those are consistent charges. So you don't have to stress on that. Theoretically, yes. You don't have to worry about it.
So are solubility rules something that we just need to memorize?
So, yes and no. As was just pointed out, you do have a note card. When you go through and work your solubility rule problems, you'll start to pick up patterns and you'll start to memorize certain ones. I will freely admit that I don't have hardly any of these memorized. But in my defense, I don't like general chemistry, so. So, which ones do I have memorized? Nitrate, acetate, and interestingly enough, they don't have the only other rule I've got memorized. Look at that. All those rules, and I only have 3 rules memorized. And one of them wasn't even on the table. Okay. Why do I have those 3 rules memorized?
Because they're the most common.
They are very common. There's another reason why.
They're all soluble. With everything. They don't have
There are no exceptions to those 3 rules. Okay. I have a horrible time memorizing things, so I will pick the ones where there's few exceptions as possible, and I'll stick with those. Okay. Those 3 you should absolutely know like the back of your hand so that you can go through and apply them very, very quickly. The rest of them, you will probably need a table. You can use your note card to try and pick those out. I actually forgot. This is my fault. I was going to print that. So I'm going to print that sheet because it's going to be very helpful for lab that you're doing today. Your entire lab today is based off of solubility rules. Right? So if you don't have the solubility rules handy, that's going to be problematic. So one of the things that I will try and do, as we kind of, I'll pause them on it. My recording just freaked out. That was one of the rules I told you to memorize. What about the next one? Could look to the chloride, but I would preferentially look to that potassium ion because potassium is a group 1 metal, always soluble. So cool, good job. You guys did the hardest part of this question. You solved solubility by looking at your solubility rules. Was there an easier way? Oftentimes there is. They're both aqueous. What does that mean? They're both soluble by definition. It's in the question. Okay? It's given to you. Okay? Nice. Take advantage of that. So when we go through and do this transposition, what we're saying is we're taking our ions and we're exchanging them with each other. Okay? Which ion do you want to look at? The anion or the cation? I heard anion, I believe. What was our anion in silver nitrate? The nitrate. What was our anion in potassium chloride? Chloride. Once you've decided on one to swap, swap them. What do you get as a result?
Silver chloride.
AgCl plus
Potassium nitrate.
potassium nitrate. Soluble, insoluble?
Insoluble.
This one's insoluble. And the next one is
Soluble.
soluble. How'd you guys figure that out?
Because of the nitrate.
So we could look at the potassium or the nitrate to classify that compound as soluble. For our silver chloride, how'd you decide it was insoluble? Silver was our exception to chlorides. Was there an easier way? What was that easier way? Identifying if there's a precipitate is what we're trying to do here.
Doesn't it mean if you have one soluble, doesn't that mean the other one's insoluble?
No, that does not mean that. Not a bad idea, but we definitely throw that curveball out there to make sure you don't just trigger that. On that first case where we looked at the silver nitrate and the potassium chloride, what was the easier way?
The aqueous.
You looked at the phase. What just made this question a lot trickier?
It is nothing.
No phase was specified. You had to predict it. You have to bring that information. There isn't an easier way. You have to go through your solubility rules. How can we make life easier for the next person down the line looking at our work?
Right down there.
We could include the phases. What is our phase for an insoluble compound?
Solid.
What is our phase for a soluble compound? Aqueous. Yes.
Would gases be considered insoluble?
Yes.
Okay.
Ish. Enough. So, in the case that they went through and did, oh man, I don't know why they highlighted it like that, but they did. So that's how your textbook went through and did it. Okay, they highlighted the silver and the chloride, they brought those two to each other. All we're doing is doing that exchange. Does it matter which one I started with? What if I had decided to transpose the cation? Would I have gotten a different answer? AgCl is definitely not KNO3, so that has to be a different answer, right?
No,
You just switch them.
Addition doesn't matter the order in which you do it. Okay? So both those answers end up being the same. Officially, you need to add your phases. So that would be a solid, right? Because it was a solid above, and that one would be aqueous. Don't just assume. Our potassium nitrate was aqueous. Our silver chloride was a solid. Okay? Questions? Don't look too excited. You're making me get really happy. It's Monday. Fair enough. So, now we can run into this next concept of classifying our different equations. What we just looked at is what's known as the molecular equation. It's known as the molecular equation because what do we have at the bottom? Molecules. We put everything into the molecular form. Okay, so that's our molecular equation. That's the most common one that you see. We can also convert this across to the ionic equation. What's the difference? We've got the ions. Why can we draw in ions?
Because they're not bonded. They have an ionic bond, but they're Yeah, they're aqueous.
They're aqueous. There's your easy answer. So when we started, we had AgNO3 aqueous plus our potassium nitrate aqueous goes across. What do we form? Our silver chloride solid plus our potassium nitrate aqueous. That says AQ at the back. Okay. Whoops, not potassium nitrate, potassium chloride.
Yeah.
Thanks for pointing that out, guys. I did see it. So, we can then split anything that is aqueous into the ions. So you'll notice that our AgNO3 turned into Ag plus and NO3 minus. Our potassium chloride turned into K plus, Cl minus. Our potassium nitrate, on our product side, nitrate and the potassium. What happened to the silver chloride? Why did I not separate that into the ions? It's a solid. The only ones that you can split into ions are aqueous. Only ones you can touch. So do not touch anything with a solid phase. That must stay constant. Yes?
Do we have to put the order? Because I know addition, the order shouldn't matter, but like because it's Ag and O3, we should put those next to each other when doing.
Because it is addition, the order does not matter at all. In general, you will notice that if we started with AgNO3, the very first thing that shows up will be the silver ion. The very next one will be the nitrate ion. Why did I not show the potassium ion first?
Silver and potassium weren't combined to start with?
But remember, the order of addition does not matter. It does not matter. We could have done it any order we want. Why did we pick this order? It's easier. That's it. That's all it is. Okay? We format things so that we can see as cleanly as possible what's happening in the next step. Okay? This is why when we do dimensional analysis, we try to write it out as one big line. We don't do it as multiple steps, because every time you do a step, you can potentially make a mistake. So what we're trying to do is not do any transpositions at first. Just drop it immediately into the ions. Keep those as simple as possible. Okay? Yeah, we already said that. The next part of this is looking at the equation and saying there's an awful lot of junk to write there. Okay? And that gets a bit tedious to go through and write out. So what we want to do is simplify. How can we simplify? What happened to the silver ion in the course of this reaction? Became a precipitate. So did it do something? Yeah. What happened to the nitrate ion? Absolutely nothing. I started with nitrate ion, I ended with nitrate ion. All right, well, if it does absolutely nothing, should we even discuss it? Let's cut it out of our equation. So we can cancel across the equation. What about the potassium ion?
Same thing.
Same deal. What can we refer to those ions as? Those are our spectator ions, right? Because they're watching the reaction occur. We don't really care about them, so we tend to ignore them. And we can simplify this down all the way to the equation of Ag plus with its phase. What was it? Next, chloride with its phase goes to silver chloride and its phase. Relatively straightforward. What we now have is what is known as the net ionic equation. Okay. Can you skip going through the total ionic equation?
Yes.
Yes and no. How good are you at balancing?
Right.
Okay. Some of you are already shaking your head no. Don't skip the net ionic or the total ionic equation. Okay. The more steps you skip, the more likely you'll make a mistake. Okay, so don't skip it. I will say also that I know Dr. Wood wants to reinforce this aspect of going through and drawing out your total ionic equations. And that means when you get into lab, you know that lab sheet? I'm going to steal this from you real quickly. That lab sheet, that's the pre-lab, isn't it?
No,
You didn't have it figured out?
the lab last week.
Oh, okay. So those of you that did it last week, you got all those things in it, right? You had to come up with all those equations. You had to draw the molecular, the total, and the net. Why? To beat it into your head on what's going on with this process. The more repetition, the better off you'll be. Okay? So it's interesting that you guys did it last week. I guess we should tell somebody that. We've got the net ionic equation as our next and final step, which we already talked about there. So, our general steps: write out your balanced molecular equation first, dissociate all your strong electrolytes, cross out anything that remains unchanged from the left side to the right side, and write the net ionic equation with the species that remains. Yes?
For our purposes, are they always going to be strong electrolytes?
Well, in that previous question, oops, oh man, I hate slides like this. Silver chloride, weak or strong? Okay, so it's not always a strong electrolyte. So what you should be focusing on, instead of saying, I'm going to step through all that junk. Instead of saying our strong electrolytes, what should we change that to? We can't say all electrolytes, that's a bit difficult. So how did we decide in the previous equation that we could dissociate some of those ions?
Because they're aqueous, right? And we're dealing with aqueous. So
Dissociate all aqueous phases. Now you can completely ignore the electrolyte aspect. You can focus on that aqueous phase. Okay. I'll do a quick example. I'm not good at thinking on my feet, so let's see what happens here. I need another one. What do I want to react this with? Oh, that's going to be problematic. Let's just fix this. And I think I can get away with this one. Phase for sodium carbonate. Aqueous. How do we know that? Okay. Sodium or anything with a group 1 metal is soluble. Calcium chloride. That's what I was hoping it was. Is it actually?
I think so, you know, but,
Because anything with chlorine is soluble except for.
Oh yeah, that was silver, mercury, or lead. So I think I dodged a bullet there. What happens as our product?
sodium chloride and calcium carbonate.
I'm okay with the weird looks. What's wrong with this? All I did was transpose, right? I took the calcium, exchanged it with the sodium to get calcium carbonate. Why can't I move the subscript? I moved the subscript on the carbonate.
Well, this carbonate's a polyatomic ion.
Why is there a 3 associated with carbonate? That is what makes carbonate carbonate. 3 is part of the symbol carbonate. Why is there a 2 written with the sodium? To balance the carbonate. The symbol for sodium is Na, period. Which means when I go through to do my substitution or my transposition, it is going to be sodium with the chloride. Okay. Same deal with that 2. Why is there a 2 with calcium chloride? To balance out the calcium. So what I've done is my transposition. I now have my sodium and my chloride next to each other. How many sodiums do I need to balance out the chloride?
1.
1 of each, because the charge on sodium is +1. The charge on chloride, -1. When you predict your products, you must first predict the product, then worry about balancing. Make sure your product is correct. So we get sodium chloride plus our calcium carbonate. Okay. Why do I not have any numbers with our calcium or our carbonate? They're balanced. The charge on calcium is +2. Carbonate is a -2. Still seeing some puzzled faces, so let's draw out those charges down there. Now, is the equation balanced? No. Now you have to deal with balancing the whole equation. But you don't want to start balancing the equation if your formulas are wrong. Okay, so you have to make sure you predict your products correctly. And if I did this right, our sodium chloride is aqueous and the calcium carbonate is solid. Yes. We're done.